Hello, and welcome to Lecture 5 of Electric Interactions in Phys 1204. This lecture is largely going to be worked examples. Before I get to working those examples, though, I just want to set some context by looking back at what we did in Phys 1104 and looking forward at what we're going to do in this course. First of all, note that the electric force is just another force, and it is just like every other force. And so everything that we know about forces from Phys 1104 still applies. In particular, we know that the equation of motion has to apply. And so we will be interested in vector sums of forces, in particular vector sums of electric forces. All Coulomb's law has given us is a way of calculating electric force vectors. The elephant in the room, though, is this r hat vector, and so let me just take a moment to explain why we need it. Think about a charge q1 being carried past this charge q2. I say carried past because it's being repelled by q2, and so if the electrical force due to q2 were the only thing acting on it, it would move in a curved path, something like this. So there must be some other forces acting on it here, but don't worry about that. I want to just talk about these electrical forces. Notice that as q1 moves past q2, not only is the magnitude of the electrical force changing, but because it always points directly away from q2, its direction is changing as well. So not only is the magnitude of the electrical force a function of position, but its direction is too, and r hat here gives us a way of writing that function. Contrast that with about the most complicated sort of situation we saw in Phys 1104, where once this block starts sliding up the slope, we would have a free body diagram like this. We could set axes, and all of our forces would be parallel to some axis or another, except for a constant force pointing in a constant direction. Things are more complicated now. Just like in this situation, we have non-constant forces, and so the equation of motion, except in a static situation, won't be very useful. But we know how to deal with non-constant forces. We use work and energy, and so that, eventually in this course, will be our main path forward. Let's start off with a very easy calculation and just find the size, the magnitude of the electrical force exerted on a chloride ion by a sodium ion. So let's say these are in solution. It would be fairly common in a solution, a salt solution, for these ions to be about a nanometer apart. And I'll just note that we're ignoring lots of things. There would be water molecules all around these, and those would all be polarized, and so they would be exerting electrical forces, and there would probably be hydronium ions and hydroxide ions all over the place as well. So we're not trying to find anything like a total electrical force on this chloride. We're simply concentrating on the force that this sodium ion is exerting on it. And so this electrical force, these really are more or less point charges. They're not really, atoms are not points, but on this length scale they are. And so we can use Coulomb's law to find that electrical force. And note those absolute values. So I do not have to worry about the fact that this chloride ion is negatively charged. I simply have a Q sodium, which is E, and a Q chloride, absolute value, which is also E. And so that's all I have. So that is rather easy to calculate now. And I'll note that a nanometer is 10 to the negative 9 meters. And the units all work out. Meters squared takes out meters squared, coulombs squared takes out coulombs squared, and so I will get newtons in the end. And we get an answer of order 10 to the negative 10 newtons. Now, that seems like a very small force. Let's now calculate the gravitational force on this chloride ion. Well, that's easy. That's just mg. And the mass of a chloride ion is this, and so that is just going to be, G is basically 10, and so this is 5.8 times 10 to the negative 25 newtons. So note that the electrical force on this chloride ion is about 15 orders of magnitude larger than the gravitational force on the chloride ion. So this is in general true that on molecular scales, and even on scales rather a lot larger than molecular scales, such as on the scales that bacteria exist on, gravitational forces just don't matter. The electrical force is all we have to worry about. Another thing to notice is that if there were not all these other things exerting forces on the chloride ion, and if it was just interacting with this sodium ion, what would its acceleration be? So let's say our electrical force is the mass times acceleration of the chloride ion. This is only valid if the only thing it's interacting with is the sodium ion. Well, that acceleration, if you just take this force and divide by this inertia, you're going to get something of order, look, 10 to the negative 10 divided by 10 to the negative 26, 10 to the 16 meters per second squared. When we accelerate ions with electrical forces, we tend to end up with truly enormous accelerations. Before I go on and work some more complicated examples, you should check that you know how to think through the directions of electrical forces on charges. So here are 3 charges, 1, 2, and 3. And what's shown in the diagram are the interactions between charge 1 and the other 2 charges. And we're going to figure out what the direction of the total electrical force acting on charge 2 is. I'll give you 2 hints. One is that we don't know the signs of these charges, but we don't need to. We have enough information here to figure this out. And the second is that not all the forces acting on these charges are shown. We only care about the electrical forces, but we don't even have all the electrical forces on the diagram. All we have are the electrical forces due to the interactions between one and the other 2 charges.